All right, hopefully I have enough battery to get us through this. Oh, that's not where I was. So we are going to cover hydrates now. So remember your last worksheet, your 7th worksheet. So worksheet number 7 is practicing this. Hydrates are basically just finding an empirical formula for something that has water in it. So some ionic compounds are capable of holding water. So think about if you are well hydrated, what does that mean you have? It means you have water. So that's what hydrates represent, that they are ionic compounds that can hold water. Not all of them can hold water within their structure like this. They can hold H2O in between their crystalline structure. Now, because they can hold the H2O in between their crystalline structure, it actually changes their color. So a hydrate and an anhydrate are going to have different colors. And that's how we can tell, like in lab, how it has lost its water. So hydrate is our term for with water, and anhydrate is what it means to not have water. So without H2O. Okay, so those are our 2 vocab words for this. Now, if you ever heard of anhydrous ammonia, that is referring to something farmers use a lot, and that is meaning it doesn't have its water in it. Now, the reason we have a unique way of writing this is because you can't write, like, if it was copper 2 sulfate, hexahydrate. I'm making these up. Okay, if this were the compound, this is our salt, and this is how much water it can take. Now, the reason we can't write CuSO4 plus 7H2O is because that would represent a chemical reaction according to chemical nomenclature and standard practices. We also can't write CuSO4 7H2O because, first of all, we never put a coefficient in the middle of a formula. Okay, that doesn't work. And we also would be saying that it would take chemical means for this to separate because we chemically combine together. And that's just not the case. We can actually vaporize that water off by heating it. And again, that is what you'll be doing in lab. So for that reason, we just have a very unique way of writing it, and that's CuSO4 dot 7H2O. And what that means is 1 part copper 2 sulfate to 7 parts H2O. Now that means every single time that is the max that that compound can hold. They all have a unique value for how much water they can hold. So let's go ahead and do some problems. Okay, I'm going to erase this and do this first one with you. All right, so hopefully my battery doesn't die. I like to highlight my hydrates and my anhydrates so I don't start flipping them around because it's a very easy thing to do. And the other thing is to think about it, what's actually happening here. So you have hydrate of magnesium sulfate. So picture you have a little evaporating dish that has your magnesium sulfate in it. Okay, it's got magnesium sulfate hydrate in it. So magnesium sulfate as a hydrate, meaning it has water. And then you're going to heat it and cause all of that water to come off that you can get off. Okay, so what's going to happen is water is going to come on out, so H2O comes on out. Again, the reason is because your ionic compounds, like magnesium sulfate, have a very high melting point. So when you put it under the Bunsen burner flame, we know they're not going to melt. Remember, think back to our last lab. But what does happen is the water is going to vaporize out because water is going to vaporize at 100 degrees Celsius. And that flame is about, well, a few thousand degrees Celsius. So plenty hot for that water to come out. That's why it's going to crackle when you do it in lab. When this happens, we'll see a color change, yada, yada. Okay, so this is what happens. So we start with magnesium sulfate dot something H2O. And then when we're done, we're going to have magnesium sulfate as a solid in that dish left over, and H2O chilling in the air okay, as a water vapor or liquid. So it's going to come out as a gas first. Okay, but here, this whole thing is as a solid. So this is basically what happens when you heat it, okay? So we got to figure out this guy has a mass of 13.52 grams. There's no water left in it, so it's magnesium sulfate, and that's called the anhydrate, right there. And they're saying his mass is 6.60 grams. So if this guy has a mass of 13.52 grams, and he splits up into these two guys, this 6.60, what had the mass had to have been? Well, you take 13.52 minus 6.60, and we realize that that mass had to have been 6.92 grams. All right, so I'm going to erase this so I can write my equation there. The actual problem we're going to be doing. So we're going to say then is if we're starting with 13.52 grams of MgSO4 dot something H2O, and I'm given that there's 6.60 grams of magnesium anhydrate, so the dry stuff when it comes out. I want to know how much water came out. Well, I just subtract that, and I get 6.92 grams of water came out. Now, to figure out the ratio, I'm just at the point where it's just like the empirical formula. We got to figure out that SI base unit of amount of substance and use that as a ratio. So I look to the periodic table, and if I have 1 mole of magnesium sulfate, how much do I have in grams? And in 1 mole of H2O, what do I have for a mass? 18.015 grams of H2O. And magnesium sulfate, you just add up 1 magnesium, 1 sulfur, and 4 oxygens, and you get a mass of 120.367 grams. 120.367 grams. All right, then on your periodic table, you're going to take 6.60 divided by 120. Sorry, on your calculator, goodness gracious. And record it out to 3 digits here, 0.0548. We were given 3 sig figs in the given, so I'm going to use 3 now. Moles of magnesium sulfate. And then here, 6.92 divided by 18.015 gives me 0.384 moles of H2O. Now remember, just like the empirical, we want to figure out this ratio. This is true, but it's not a whole number. We can't just throw that number in there, right? So what we have to do is divide by the smallest, because then we can figure out how many times bigger is the water than our smallest. And we set the smallest to 1. Now this should come within a tenth, okay? If it doesn't, you got to do more strategizing, just like with empirical, but this should always come within a tenth for this one for you. They come out a little cleaner here, so we ended up with a 7 for the H2O, which is why your final answer, which I've written up here, the formula is magnesium sulfate heptahydrate, so 7H2O, and then you say it like this, magnesium sulfate heptahydrate. Remember, those prefixes are in your periodic table. They're the same as the nomenclature for covalent compounds, and then you just say hydrate, because it is a hydrate. All right, same process every single time. So here they're telling us that a sample of copper 2 sulfate hydrate has this mass. Okay, so that's the one that's wet. And then we heat it, and the dry stuff has this mass. So what we do again is we take this one minus this one and discover there's 1.43 grams of water. Now, to figure out the ratio of the salt to the water, I take the salt, the ionic compound, convert it to moles. I take the water, convert it to moles, just like your one-step conversions. Divide by the smallest, just like empirical formula. And then you'll get a whole number ratio. And then you'll take your 1 part for your copper sulfate and 5 parts for your H2O. And then we can say that our copper 2 sulfate pentahydrate has this chemical formula and this chemical name. All right, this problem, number 3, make sure to pause me if you're not here yet. Number 3 is saying that you've got 5 grams of your wet one, the hydrate, but they this time told you 2 grams of water came off. Okay, so this is the same but slightly different. They just gave you the other number. So if we're starting with 5 grams of iron chloride and 2 of it's water, then that means 3 of it was iron chloride and 2 of it was water. Okay, then we just convert to the SI base unit of each of those and then compare those by dividing by the smallest. And we figure out that we have a 1, 2, did I not do that? Let me see, did it die on me yesterday maybe? Probably on 3. Right, I'll divide it right now. So 0.111 divided by 0.0185, it comes out to about 6. I don't know why I wrote monohydrate there. Oh, that's for the problem below. Okay, that's the problem beneath this. So I'm going to erase that here. Oh, that's a big eraser. All right, so then the chemical formula means I have 6 parts water for every 1 part of my salt. So it's 1 part iron 3 chloride. That X here is just saying how many waters will I have? 6 parts H2O. It's a variable saying my unknown. And then we say that as, let me scooch them over so I can have room to write it. These are kind of long. Iron 3, and I can tell that because of the 3 behind the chloride. Chloride is 1 minus. Iron 3 chloride hexahydrate. All right, and that is your final answer for that one. Number 4, a sample hydrate sodium carbonate. So your wet sodium carbonate has this mass, and it loses this much water. So very similar to the one above. Number 2, this time you just take your big number minus little number, and this time they're telling you their water, and that number is going to actually give you your sodium carbonate. Now make sure that you remember that carbonate has a 2 minus and sodium has a 1 plus, so you need 2 sodiums. And then just like always, you're going to convert from your water and your salt to moles of water and moles of salt. Divide by your smallest. They come out to be about a 1-to-1 ratio. Therefore, here it is. I'll accept it with or without the coefficient in front of it. Either way is fine. But you should say this as sodium carbonate monohydrate. And yes, you need to say mono. All right, now this one is telling you that the sample, when it's wet, the hydrate has 16.4 grams, and it's heated until all the water's off. The calcium sulfate that's left has 13.0 grams. That means you lost 3.4 grams of water. So we're going to take the 13.0 grams of copper sulfate that they gave us and convert to moles of calcium sulfate. And you found it to be 3.4 grams of water by subtracting those two, and convert to moles of H2O, and you find it's a 1-to-2 ratio. So you say calcium sulfate dihydrate. All right, number 6, the only thing here that made it look a little bit more complicated was the way they said it. They have 8.0 grams of lead acetate, and say dot X H2O, just like before. It's how much H2O, you don't know, are heated, and 1.14 grams of water are driven off. So H2O is what's given to you. So this time, you are going to have to figure out the salt's mass by subtracting them. So your hydrate has this much for mass. And your water is 1.14 grams, therefore your anhydrate is 6.86 grams. And then you're going to take 1.14 divided by 18.015 and record it through SigFig, so 0.0633, I had to round up, moles of H2O, and 6.86 divided by 298.242, and you get 0.0230 moles of lead, C2H3O2, lead 2 acetate. Now I'm going to divide by the smallest, and that means I'm going to divide them both by 0.0230. So that one's 1. So 0.0633 divided by 0.023. And I get let me type my numbers again so it looks finicky. 1.14 divided by 18.015. Divide that by 0.023. Yeah, 2.75. Really didn't think we'd have any with a higher ratio. This helps us out. Which number of mine is 20? 6.86. Oh, it's 3. What did I do here? How did I even pull that? That mass is completely random. I hope you were saying, what on earth are you doing? Okay. It wasn't coming out to a nice number, so I was getting confused as to why that wasn't working. And my reason is because this is the mass PB C2H3O2. Alright, so 6.86 divided by 323.288. You get 0.0295 moles of lead 2 acetate. And divide both of them by the smallest. So 0.0633 divided by 0.0295. 2. There we go. That's not what I got. Hold on. Oh, I did the. Gosh darn it. What on earth? It's 6.86 divided by. Goodness. Fat fingers again. 6.86 divided by 328.288. There you go. That's what it should be. All right.